All right. This is going to be an example problem focused on chapter 17.3 or section 17.3 on the translation of rigid bodies. This object, when pulled in this fashion, is capable of not rotating. It's true that if you pull it hard enough that maybe it will start to rotate, but this force is not large enough to make that happen. So we have to analyze the system from a sum of the moments perspective such that there is no rotation. We have two equations that are useful. The sum of the forces is equal to the mass of the object times the acceleration of the center of mass, and the sum of the moments about the center of mass equals the moment of inertia about the center of mass times alpha of the object, which is 0. We could also use a different version of this equation if we like, which is the sum of the moments about any point is equal to r, g with respect to O, crossed m with a of g. And I am probably going to use this one. I should probably say this has a plus ig alpha, but of course, since alpha is 0, I probably will not. Well, since alpha is 0, we don't need to consider it. The reason I'm likely going to use this equation is it's more convenient. I can sum the moments wherever I want to. And I find that valuable because this problem is going to have known forces and unknown forces. And, well, let's work through it, and I'll talk about it as we get there. So let's draw a free body diagram first. I'm going to draw it directly on the image. As far as forces acting on this object, I have a normal force on the ground at B, or from the ground. I have a normal force from the ground at A, and I have the weight force. I could draw that a little better, don't you think? The weight force that points straight down. And then I have this applied force, so don't forget that one either. Those are the four forces acting on the object. I anticipate that this thing is just translating left and right. So when I work on this equation, I need to think about x and y components, or rather, sum the forces in any two directions you like. So let's start. Summing the forces in x, I simply have that 600 newtons is equal to the overall mass, which it gives me here, 150 kilograms, times the acceleration of g in the x direction. If I sum the forces in the y direction, I have the normal force at A plus the normal force at B minus the weight, which is 150 kilograms times 9.81 meters per second squared, equals the mass of the object, which I don't have to leave as a variable, 150 kilograms times the acceleration of g in the y direction. And then, well, let's consider these two equations first, in particular the y equation. We need, when thinking about this, to think about motion. What do you anticipate the motion of the cart looks like? I anticipate this thing is just moving to the left and right, a straight line path. And if g travels in a horizontal straight line path, then the acceleration in the y direction is 0. It's not moving up or down at all. So that means that this is all 0. Now let's think about summing the moments. I would like to sum the moments about a point. Which point? I'm not sure yet. I can sum the moments about point G and use this equation, but I'm not so sure I want to. It would work. There's nothing wrong with it. Let's do it both ways. So I'm going to use the top equation first. Let's sum the moments about point G. So if I sum the moments about point G, I get the following. I'm using the right-hand rule visually, and you can't see it, so that's useless. About point G, NB creates clockwise rotation, so I'll say negative NB. It's a vertical force, so I multiply by the horizontal distance of 0.75 meters. NA creates counterclockwise rotation, positive. NA times its distance, which is 1.25 meters. Then we have P which is, let's see, there's 1.25 from G to the ground and 0.5 from the ground up to P, so there's 0.75. It's also creating counterclockwise rotation. So 600 newtons times 0.75 meters. And that's all equal to 0. What I see in these two equations is a two equations, two unknowns situation. NA and NB both appear in the equations. So I can solve those. Two equations, two unknowns. Additionally, here I have only one equation, one unknown. So this problem isn't so bad. Let's talk about AGX first. AGX is equal to 600 newtons divided by 150 kilograms, and that's equal to 4 meters per second squared. And I know I didn't focus on this very much, but they did ask me for that. Determine the trailer's acceleration and the normal force on the pairs of wheels at A and B. So there you go. We have found the acceleration. Next, I need to consider these two equations, again, these two, so that I can determine the normal force reactions at A and B. It's two equations, two unknowns, so it's kind of up to you how you want to deal with this. What I'm going to do is multiply this equation by 0.75 and add it to the bottom equation. Hopefully you can see what that will do. NB times 0.75 minus NB times 0.75 will cancel out, and I'll be left with just NA. So when I do that, I get, let's see, 0.75 NA plus 1.25 NA minus 150 kilograms times 9.81 times 0.75 plus 600 times 0.75. On the right side, we have 0 for both, so just 0. This tells me that NA is equal to 150 times 9.81 times 0.75 minus 600 times 0.75 divided by 2, which equals, let's sort that out, 150 times 9.81 times 0.75 minus 600 times 0.75 divided by 2. Oops. Parentheses and balance. Okay, I got 326.8 newtons, which, based on the sum of the forces in Y equation, is going to tell me that NB is equal to 1145 newtons. Those are my many equations. And it's true, if we accelerate by applying a force below the center of gravity, that puts an additional load on the rear wheel. If we applied a force that was above the center of gravity, then we would apply a larger force on the front wheel. And if we apply this force large enough, then NA will go to 0, and that would be bad. I should say, well, I shouldn't say large enough. I think it would have to be low enough, but I'm not willing to go to all the lengths to calculate that right now. But it's true that with enough force applied in the right place, we could have rotation in this problem. We would see that if we solved for the normal force and it was negative. If we had a negative normal force, we would look at that and say, the ground cannot exert a negative normal force on the wheel, therefore this situation is rotating, and we'd have to start the problem over again. Analyzing this problem with rotation and no normal force at A. One additional unknown, alpha, but one fewer unknown, NA. So it just becomes a new problem with a different set of unknowns. But we have our answers. We have the acceleration in the x direction. We have the normal force of the two wheels. So that's that. All right. I want to solve it the other way using this equation. I think it's a little easier, and I'll do that on the following page. So I'm going to go to a new page. I'm going to insert that photo. Unfortunately, it took the entire page, so I need to edit it down. I didn't anticipate having to do all this, but here we are. Oh my. Come on. There we go. Seems good. Apply. Done. Bring it up. Make it big. Okay. Same problem. And now I'm going to do the exact same thing. So sum of the forces in the x direction equals 600 newtons, and that's equal to 150 kilograms times the acceleration of g in the x direction. Sum of the forces in y, same thing, is equal to NA plus NB minus 150 kilograms times 9.81 meters per second squared equals the mass times the acceleration of point G in the y direction, but we know this is 0, so we don't really worry about it. Then I'm going to sum the moments about specifically point B. If I sum the moments about any other point, I have to do m, well, let me write it this way, r of g with respect to O crossed with ma of g plus ig alpha. Of course, in this problem, alpha is 0, so I'm not so worried about that. We just have this part of the equation. This is kind of familiar, and I want you to think about it like this. I want you to realize how much r cross ma is like r cross f. R cross f is moment of force, and you know how to do that. You've been practicing that since Engineering 106. You've done it a lot in statics class. R cross f, especially for 2D problems, is something you have some intuition. So you just have to think like about ma like it's a force, and use that to calculate the moment it creates. Be careful though, this moment appears on the right side of the equation, not the left. So it's not a force, and it's not a moment of force. It belongs on the right side. The book calls this a kinetic moment, and that's fine. If you try and search for kinetic moments online, you won't find a lot of results. This is something that's pretty unique to the Hibbeler textbook, and other textbooks don't use this term in my experience. But anyway, they're trying to allude to the fact that you can think of this like a moment of force. So that's what I'm going to do. I know that AG is accelerating to the right, so I'm going to draw a little arrow here, AGX, and I could also draw an AGY if I wanted to. I know it's 0, so I'm not too worried about it, AGY. And I'm going to think about the moment that acceleration creates about point B, which is this point at the bottom of the wheel. All right, so some of the moments about point B. First of all, let's focus on the left side of the equation. This has nothing to do with the acceleration. What forces create a moment about B? Well, there's the weight force still, and there's the normal force at A, and there's the applied load of 600 newtons to the right. So some of the moments about point B are 0.75 times 150 kilograms times 9.81 meters per second squared. And it's clockwise, so negative. I have NA, which is 2 meters away. 2 meters times NA. That is counterclockwise, so positive. And then there's a negative, a clockwise rotation created by P. It is 600 newtons times 0.5 meters. And that's equal to, the right side of the equation is this thing I've circled up above. I'm going to go ahead and erase all those circles, but that's equal to r cross ma. I know that it's just accelerating to the right, so I'm going to ignore this AGY. This is just force times distance, and the acceleration is horizontal, so the distance I'm worried about is the vertical distance. What's the vertical distance between B and G? It's 1.25 meters. This, if it were a force, would create clockwise rotation about B, so it's negative 1.25 times ma, and the mass is 150 kilograms. And the acceleration as of right now is unknown, solving the problem this way. But this pathway is now very straightforward to the problem. From the first equation, we find that AGX is equal to 4 meters per second squared. We take that result and plug it in here. Then this equation has only one unknown, NA. And if I solve for NA, I will find it is equal to, pardon me, I can do this, 0.75 times 150 kilograms times 9.81 meters per second squared plus 600 newtons times 0.5 meters minus 1.25 meters times 150 kilograms times 4 meters per second squared, which is AGX. That all divided by 2. I'll throw that into my calculator just to humor myself and honestly check my work from before. I don't have a solution in front of me except for the one I've written, so let's see if I do it this way, if I get the same result. 600 times 0.5 divided by, minus 1.25 times 150 times 4 divided by 2, fingers crossed, I get 326.8 newtons, which, if I go to my previous result, it's the same as before. So, the important thing here is, if you want to sum the moments about a point that is not the center of mass, you must consider this term. The sum of the moments is not 0. This isn't a statics problem. The fact that the center of mass is accelerating has an impact. Really, it's a fact that the sum of the forces is not 0. The forces add up to not 0. So you can't sum the moments about different points and get the same result each time. Changing the point changes the moment, changes the motion. Anyway, if you have any questions about the solution, feel free to ask me. But that'll conclude this video. I will be posting a couple of examples for general rotational motion, so keep an eye out for those.